Alright, so here I've got a plot and an equation. So the plot shows pressure versus specific volume. So how the pressure changes as the volume changes at a specific temperature. So all of these dotted curves are at different temperatures, and this solid black curve here connects all of like these discontinuities, basically. And so you may wonder what's happening in the middle here of this black curve. So in the middle here is nothing really relating to reality. Basically at like say this pressure right here, you've got a mixture of liquid and vapor, and then liquid has a specific volume of this, and the vapor has a specific volume over here, and that substance doesn't have any phases with a specific volume between the two, because there's no phases between a liquid and a vapor, so it kind of just jumps past that, the curve does. So looking at this, you'll notice that these are obviously non-ideal curves. And so that's where the van der Waals equation of state comes into play. So the van der Waals equation of state is a correction of the ideal gas law. It corrects for two main assumptions that the ideal gas law makes. The first of which is that molecules within whatever gas you're looking at do not have any volume. So the volume is negligible compared to whatever container they're in. Of course, it's not always realistic for a real-life scenario. So van der Waals included this term B here, which is the excluded volume, and basically just the volume that the gas takes up. So the other assumption that this corrects for is the assumption that gases do not like see other molecules of gas, and that they don't feel like attracted to them or repulsed by them. So obviously in real life there will be polar compounds that will feel attracted towards each other, and which will alter their paths, make them collide with the walls of the container less, which will decrease the pressure. And so that's why we have, or van der Waals has this term up here with an A that's subtracted from the total pressure, because that accounts for these attractive forces. So A and B are going to be constants, and they're going to be different for every compound that you look at, substance that you look at. So we need a way to easily solve for both A and B for a compound that you have. So looking at this plot up here, you can see that there's one curve, this one right here, that hits this solid black curve at exactly one point, and this point is the critical point, so critical pressure, critical volume, critical temperature. And not only is this just the critical point that hits the curve in one point, it's also an inflection point, because it's concave up there, concave down on that side. And that means that the derivative and the second derivative of this equation at that point are both equal to 0. So if we take the derivative of this, set it equal to 0, take the second derivative of this and set it equal to 0, we have two equations and two unknowns, and we can solve for A and B algebraically. So that only works for the critical pressure, critical volume, and critical temperature. So, you have to, instead of just T, you have critical temperature. Instead of just V, you have critical, you get the idea. And so that is how we would solve for A and B of any compound that you have. Alright, so I'm going to show you how to find A and B for the van der Waals equation of state using the critical temperature, or the critical points, the critical temperature, critical volume, and critical pressure. So you'll remember that the first derivative and second derivative are both equal to 0, so we can write that out. So we've got, so partial derivative of the pressure with respect to the specific volume at a temperature equal to the critical temperature, and the specific volume equal to the critical volume. It's going to be equal to 0, so now we can just take the derivative of this. So it equals negative R times the temperature over absolute volume, or B minus B squared, so specific volume minus excluded volume squared. Alright, so minus 2a over specific volume cubed. All of these are at the critical point, so I'm going to use the subscript C to denote that. Alright, and then same with the second derivative. So second derivative, that's not how you do that. So second derivative of pressure with respect to the volume. Again, we're going to be temperature at critical temperature, specific volume at the specific volume critical, at the critical point. Sorry. Okay. We're going to set that also equal to 0. So we'll take the derivative of this, and we've got 2 r times temperature over specific volume at the critical point minus b cubed, and then minus 6a, oh, that's a plus, sorry. So plus 6a over specific volume at the critical point to the 4th power. Okay. Let's see. Alright. So now let's rearrange these equations. So take that and kind of move this negative term over to that side. So we'll put that up here. So we've got R times critical temperature over critical volume minus b squared equal to 2 times a over critical volume cubed. And then for this one, we've got, I see what I did. So this one should be positive and this one should be negative. Okay. Sorry about that, because when you take the derivative, that minus turns into a plus, then you take it again, and it turns into a negative sign. I just wrote that wrong. Okay. Okay, so now we'll take this negative term over to that side. So we'll have 2RT over critical volume minus B to the 3rd equal to 6A over critical volume to the 4th. So you'll notice that like these two, you know, the left side looks pretty similar between these two equations and the right side looks pretty similar to these equations. So if we take the inverse of this equation and multiply it to that one, we're going to get a lot of stuff to cancel. So let me show you what I mean. So this one is going to turn into, so we're going to take the inverse, so just flip it upside down. So we'll have critical volume minus B cubed over 2 times gas constant times temperature equal to critical volume to the 4th power over 6A. Alright. So now we are going to do, I'm going to do this one in a different color so that you can see. So we're going to take the left side, multiply it to that side, and this right side, multiply it to this right side. So we're going to take these two first. So let's start with this one up here. And we have R times critical temperature over critical volume minus B squared, and then times this side, which is critical volume minus B cubed over 2RT. Alright, and then that is equal to, so we're going to take this side times this one, so we'll start up here. So that's going to be equal to 2A over critical volume cubed times this, which is critical volume to the 4th over 6A. So now you can see a lot of stuff is going to cancel. So on this side, R's cancel. Critical temperature cancels. This cancels. We're just left with one on the top. So that's all that cancels on that side. So we've got the critical volume minus B over 2. And then on this side, A is going to cancel. Critical volume is going to cancel. we're just going to be left to 2 times the critical volume. Or not 2, sorry, 2 over 6, so that's going to be 3. The critical volume over 3. Alright, so now we can cross multiply these. So we've got 3 times the critical volume minus 3b equal to 2 times the critical volume. Subtract that onto that side, subtract that onto that side. Got the critical volume is equal to 3b. So then b is equal to critical volume over 3. So that's how you find b. So now we can take this b and we can plug it into one of our original equations. So I'm going to choose to plug it into that one. I'll plug it into here. So that means we're going to get gas constant times temperature at the critical pressure over specific volume minus b, so we'll plug in specific volume over 3, that squared, equal to 2a over specific volume cubed. Okay. So then down here I'm going to find a common denominator, so that's going to be 2/3, so so gas constant times critical temperature over 2/3 critical volume squared equal to 2a over critical volume cubed. And then we can square this term and we'll end up with 9 bar critical temperature over 4 specific volume squared equal to 2 times a over specific volume cubed. So then we can multiply both sides by the specific volume cubed, and we're going to do so multiply by specific volumes cubed, and then that's going to cancel with that. But on this side, we're just going to be left with 1 on top. Those will cancel. So we'll get 9 times R times critical temperature times critical volume over 4 equal to 2 times A. So then we divide both sides by, or multiply both sides by 1/2, and we get A is equal to 9/8 times the gas constant times critical temperature. I don't know why I put cubed there. It's cubed. We're squared, so you just get 1 times the critical volume. And there's A. Alright, so that is how you find A and B for your for the van der Waals equation. So then these A's and B's can be plugged into this equation, and you can use it for whatever compound you have. Alright, so as you can see, I saw the van der Waals equation of state written here. I've rewritten the A and B values that we found just a minute ago over here. And then I've also added this compressibility factor. So Z is the compressibility factor. It's equal to the pressure times the specific volume over gas constant times temperature. And this is something that, so Z is equal to 1 for an ideal gas, but for a real gas, Z is not necessarily equal to 1. So what I'm going to show you how to do is how to find the compressibility factor at the critical point using the van der Waals equation and the A and B terms that we solved for just a minute ago. So first thing we're going to want to do, plug in A and B into the van der Waals equation of state and make sure that all temperatures, volumes, and pressures are at the critical point. Alright, so let's see how that looks. So we'll get that the critical pressure is equal to gas constant times critical temperature over critical volume minus B. So B is critical volume over 3. So we've got critical volume over 3. And then minus, so A is this. So we'll get 9 times R, or gas constant, times temperature, times the critical volume, over 8 times critical volume squared. Okay, so now we can simplify this a little bit. So we can simplify this denominator here, and we can cancel some volumes over there. And so we'll have critical pressure is equal to gas constant times critical temperature over, so common denominator between these two is 3, so it's going to be 2/3 of the critical volume. And so flip that up, so we'll end up with 3 pounds times the critical volume. And then minus 9 gas constant, critical temperature, that cancels, over 8 times the critical volume. Alright, so then next thing we want to do is we're going to get this kind of in the form of Z. So we have a pressure on numerator over on this side. We still need a specific volume, so let's multiply everything by the specific volume of the critical point. So 8. So we'll get pressure at the critical point times specific volume at the critical point. It's going to be equal to 3 times gas constant times critical temperature over 2, because this critical volume and this critical volume are going to cancel. And then I have 9 times gas constant times critical temperature over 8, because again, this and this are going to cancel. Alright, so what do we need next? Next we need a gas constant and the temperature on the bottom. So we're going to multiply everything by 1 over the gas constant times the temperature at the critical point. So that means that over here, we're going to get critical pressure times critical volume over gas constant times critical temperature is equal to. Alright, so this gas constant and temperature are going to cancel, so we'll just be left with 3 halves for that one. And then again, gas constant and temperature are going to cancel, so we'll be left with 9/8. So then we're just going to need to find a common denominator. So common denominator is going to be 8. So 2 times 4, so 4 over 4, and then 4 times 3 is 12. This is going to be 12 over 8, minus 9 over 8, which is 3 over 8. So I can write that out a little bit more for you guys, in case that was confusing. So we keep the left side the same, and then 3 halves is the same thing. It's 12/8, so minus 9/8. So then critical pressure minus specific volume at the critical point times the gas, over the gas constant times critical temperature is going to be equal to 3 over 8. And that is the compressibility factor at the critical point. And so the important thing about this is that this goes for any compound. Any compound has a compressibility factor of 3/8 at the critical point, according to van der Waals equation.